So up until this point, when we have been dealing with our linear models, we've talked about how to fit this line, and we thought about a residual least square fit, that is to say, a model that minimizes the residual least square fit. And in this mini lecture, we're going to do what seems like a lot of work for no reason, but we'll be able to take advantage of this later, which is we're going to talk about an alternative way of thinking about what this fit means that will give, in the case of a simple linear regression, an identical answer, but gives us a different syntax and a different vocabulary that allows us to think about how to fit these models. And this different vocabulary is going to involve a sum we'll call maximum likelihood. So we're gonna so here we have a linear model. This is from the qPCR data set that we've seen in the previous lectures. And here we're looking at the Burkholderia pathogen. So this was the one that was more linear. And as before, we have our time here and our pathogen load on the y-axis. And we have our model. So up until now, we've said this model, which is the regression line, is closer to any of these, to the data points than any other line you could draw. And we measure closeness as the distance squared of all of these fits to the model. But in this alternative view, instead of thinking about just the distance along the y-axis between the point and the model line, we're going to model all of the residuals using a normal distribution, and then use the probability density function of that normal distribution to calculate each one of these points to the probability. And then we're going to consider the joint probability of the entire data set. And then we're going to say that this regression line is the line that maximizes the likelihood. So we're going to calculate the likelihood, which is the joint probability of all of these data points converted to d-norm. And we're going to multiply them all together. And the regression line is the one that is the most likely model. Now, that's going to be, for the simple regression line, exactly the same thing. It's exactly the same regression line, but it's a different way of thinking about how we're measuring the error. Right? So let's just consider the residuals, right? So we know we can get the residuals from the linear model with the simple command residuals for any linear model. Right. And let's assume, right, in this regression model, there's an assumption that these residuals are normally distributed. So let's think about what happens when we take each one of these residuals and change it to d-norm based on the mean and standard deviation of the residuals. Now, the mean of the residuals is actually within round-off error of 0. Okay, that's coming from the definition of the regression line, right? The regression line gives you an average. Right, it splits the difference between the up and the down exactly. So this mean of the residuals is within round-off error of 0, and the standard deviation reflects the variance of the residuals, which you'll remember the regression model assumes is constant. So when I switch each one of these data points, so instead of each one of these data points being some distance from the line, we're going to consider each one of these data points as being a probability coming off the probability density function, coming off this probability density function, right? So this is all of I just take all of the residuals, I plot them out. I plot them out just into a histogram, right? If I'm thinking about them as being a normal distribution, they're centered on 0 because the regression line splits the difference between all of these points, so it's centered on 0, right? And then there's some variance which we're estimating from the data, and we're just going to consider each one of the data points here from this probability density function. And so, in fact, we're going to define the likelihood that we're going to normally use is the log likelihood, which instead of just multiplying all of the data points together, we're going to add the log. And to see why we do this, consider just a simple data set with 4 data points, just a completely made up data set, right? Consider that you have right, just 4 data points, 1, 2, 3, 4, and some regression line, right? And these 4 data points, when you change these data points into d-norm, you get these 4 values here. So just completely made up data set, right? So these 4 probabilities from d-norm are given here, right? So the likelihood of the model, remember the likelihood of the model is the joint likelihood. We multiply everything together. So if I multiply these together, I would get this number. But you can see that this number is rapidly going to become too small to hold with a standard, with a 64-bit double in R or in Java. So we would get underflow errors. So we don't want to, and it's a general rule in any probability theory that when you're multiplying probabilities together, you have to work in their logs because this would just round to 0, right? And we don't want this. We don't want our likelihoods just to round to 0 because we won't be able to work with them anymore. That'll be an underflow error. So instead of taking the product of the raw probabilities, we add the logs together. So I'm going to take the log of each one of these values and add them together. And I can do that, of course, because the log of A times B equals log of A plus log B, right? So just using the simple rule logarithm substitutions, I will get that the log likelihood of this number is this. So in general, the less likely models will have log sums that are more negative, right? So as you have smaller p-values here, this value becomes more negative, and as you go more towards probabilities of 1, this more likely model will be close to 0. So we're going to be working with these log likelihoods instead of the just the likelihoods. And the log likelihoods we can get by just summing the log likelihoods together. So this log likelihood is going to be defined by in R as just the sum of the log of all the residuals denormed with the mean and the mean and the variance of each residual, and that mean will be within round off error of 0, but we'll keep that there just because it doesn't cost us that much to calculate that, even though we know this number is going to be close to 0. So it turns out for the Burkholder-Ria data set, from a simple linear model, you get this number 108.3326. Okay, and so just to visually demonstrate this one more time, right? So for all of the 130 data points in this data set, right, we take each one of these. We make a normalization. We make we plot out all of these data using right. So this is the normal distribution using the mean of these data points, which again is going to be centered around 0, and the variance of whatever all of these variance of the data points is. Again, the variance reflecting each one of these data points, how far it is from the regression line, right? So I take that and I make a normal distribution. And I'm going to use dnorm to get each one of these probabilities. So this point here comes out to here, and so the probability is whatever I would get on the y-axis here. So this one is further away from the regression line, right? This other data point, just by example, is closer to the regression line. So the dnorm is going to give me a 0.65 here. Right, so I'm gonna do this 130 times, multiplying all of the probabilities together, just reading them off of the y-axis that I get from my dnorm. Right, and what you can see is that in the simple linear regression, right, it's the same thing. To say that this regression line is the one that gets these data points as close as possible to the top of this denorm function, which is 0, right? So it's the same thing to say that this regression line is the one that makes the most likely model, right? That gets these data points as close as possible to this point here, because this point here represents the regression line itself. So for this simple linear regression, the regression line that gets you closer, the regression line that produces the most likely model, is the same regression line that's going to minimize the residual sum squared errors. So we've introduced this vocabulary that we can think of this fit as coming from maximum likelihood, or we can think of the fit as coming from residual sum squared errors, and that's the same thing mathematically. It's just a different conceptual way to think about it. But what we'll see is that as the models get more complicated, the residual sum squared fit is not always the same as the least squared fit. And in general, it's actually going to be easier computationally to figure out the maximum likelihood fit than the residual least square fit. So when we get to the more complicated models, such as the generalized linear models and the mixed linear models coming up in the last couple of weeks of this semester, we'll see that we're often thinking about maximum likelihood fit instead of residual sum squared fit. And again, the maximum likelihood fit is just the fit. It's just the fit that gives you the most probable numbers here. So when you smush them all together, you get the probability that's closer to 1, or the sum log probability that's closer to 0. Okay. So that leads to this question now that we've defined the likelihood, that is going to lead into this question of how do you decide which models are the best. Right. So we've talked about in class, and I think you all have this idea intuitively that you can't just keep adding models to a parameter, right? So if I have 130 data points and I make a model with 130 parameters, that model is going to perfectly fit the data, but that's completely trivial. It's trivial to make arbitrarily complicated models that can match the data. Right. So how do we sort of balance this idea of whenever we add parameters to a model, we are explaining more of the variance of that model. We're reducing the variance of the model, because as we add more parameters to the data, whereas we add more parameters to the model, we're able to generate a model that will more closely match the data points. But how do we just avoid overfitting? Right. And this is not just kind of an academic question, because there have been arguments that overfitted models, for example, played a role in the financial crisis of 2008. Right, so you can make computer models of the financial market. Right, you have tons of data in the financial market. You can make models that are very, very good at describing the past by making them more complicated. But just because they're more complicated at describing the past doesn't mean they're going to do a very good job of predicting the future. And as in this Wall Street Journal article that was published a few years ago, right? This is a real argument that happens, and how you believe the way this argument comes out could determine whether you trusted a computer program to make a stock pick for you, right? So this is an argument that comes out in this literature, where there's one analyst who says, well, I can make models that can predict the future. I can make, even though it's complicated, I can use the data from the past to predict the future by making a suitably complicated but not too complicated model. And then another group of scientists that say, well, no, that's not right. You're just overfitting, right? So if you can always make models that can explain the past, but you have to but the complexity of those models means that your predictions of the future won't be any good. And again, of course, banks making bad predictions is something that is a risk to the economy. So these are kind of abstract ideas about this relationship between the complexity of data sets and the complexity of models, but they have really serious real world consequences because these models are used in so many different places in our economy. Now, of course, there's no real answer to this, like anything complicated, but there are some guidelines that you can find in the literature, and we'll look over these at least briefly here. So one is this called this AIC, this AKK, I think it's pronounced, information criteria, and I'm probably not pronouncing that correctly. So this AIC is a measure of the quality of the statistical model that tries to balance out the likelihood of a model versus the degrees of freedom, versus the number of parameters, or the likelihood of the model versus the number of parameters that are in the model. So the AIC tries to balance out the likelihood of the models versus the number of the parameters of the models. So on the one hand, for this AIC, we have a function that is based on the log likelihood. So we know that as you increase the number of parameters, right? So if the number of parameters is going up, right, then the likelihood of the equation is also going up. It's becoming less negative, or the log likelihood of the model. The model becomes more probable with an increased number of parameters. You get a model that is more closely tied to the data. So the sum residual sum squares is the residuals are closer to the model. So the log likelihood of the model goes more towards zero. So the likelihood also increases. Okay. But then if you look here, the likelihood is on this negative side. So the value of the AIC is basically going to decrease. So actually, better models are going to have a minimum here, which is what it says on the wiki, right? So a better model is one that has a minimum AIC value, because as the number of parameters increases, or as the model becomes increasingly likely, this number becomes more positive, but because it's in a negative sign, the overall AIC becomes more negative. Right? And so this is balanced out by by simply looking at the number of parameters that you had. So you're penalized here for parameters. As the parameters goes up, the AIC becomes more positive. But what you want to have is a model with a minimum AIC value. Right? So this is very easy to calculate, right? If you know the log likelihood, if you know the log likelihood, which of course we can calculate as we saw before by this sum log denorm of all the residuals, or with less typing, you can just say log likelihood. And you know the number of degrees of freedom. Now here it's 3. You might think, well, this is a simple linear model. It only has slope and intercept. But in these calculations of the likelihood, there is a third parameter that you estimate, which is the variance of the residuals. Right. So that adds a third. That adds a third parameter that's here. And so we have the log likelihood calculated either manually or calculated by just saying log like in R. We know there's 3 degrees. There's 3 parameters, right? And so just the equation that's in the slide here, we can type this into R, and we can get our AIC criteria this way, or with much less typing, we can simply do it this way. Right? And so what we're looking for, the best model in balancing out the number of parameters and the likelihood of each one of these models, the best model is the one that has the minimum value of the AIC, right? And so what we argued with Pseudomonas before, just using which model produced which parameter, when you added parameters in the previous mini lecture, we argued that that this model was the most appropriate because you got a significant reduction in the variance, increasing these parameters up to here, up to the fifth order polynomial. But we stopped having a significant increase in the variance that we could explain when we went from the x to the fifth to the x to the sixth model. So the AIC here agrees with that assessment. It doesn't see a huge difference between these different models, but the AIC model also wants to stop here, right? So in comparing all of these models, the AIC says the 6-parameter model, which is the fifth order polynomial, did the best job of balancing out the likelihood versus the degrees of freedom, or versus the number of parameters in the model. I keep saying degrees of freedom versus number of parameters, but of course it's the same thing, right? So if you have 130 data points and 6 parameters, you have 124 degrees of freedom. So you can think of measuring the parameters as either, like, as you add parameters, you have a decrease in the degrees of freedom. So it's the same thing. It's just which way you want to say it. And again, this code here just makes a little table, and so this is actually this first model here is only the mean, right? So it's just this first model here is just y equals b0 plus error, just the intercept, right? And then what we've shown a couple of times now is that in the simple model, b0 is just the mean of all the data, right? So you have all of these data points that are here, right? And then your model is just the mean is just the mean of all of these data, and the residuals is just the top part of a variance, right? So that's this first model here, which you can code up in R as 1, or you can do a linear regression only with respect to time, or we can march to the polynomial. So this is the second, third, fourth, fifth, and sixth order polynomials with 3, 4, 5, 6, and 7 parameters, right? And so what you can see is that as must be true, right? As must be true, as the number of parameters goes up, the models become increasingly likely, right? Because with a more complex model, the model can when you fit these data points, the model will become closer to the data points, and the probability, the joint probability of the model will increase, right? Which means the sum of the log likelihoods will go to will go towards 0, right? But the AIC doesn't always get better, right? So in terms of getting closer to the data and maximizing the likelihood of the model, more parameters will always make the model more likely. But the AIC says, well, okay, that's worth it up to this point. But when we get to this model here, which is the x to the 6th model with seven parameters, the balance of adding that parameter no longer justifies the increased likelihood of the model that's there, right? So this AIC criteria, again, it's not certainly a perfect way to evaluate when you're overfitting versus you're not overfitting, but at least it has some way of trying to balance out the increase of likelihood that absolutely has to happen as you increase the complexity of models, and tries to penalize that increase of likelihood by essentially penalizing you for the number of parameters that are in a particular given model. A closely related alternative is the Bayesian information criteria, really just a very slightly different formulation. These generally give fairly similar results, but we won't be going into the Bayesian information criteria versus the AIC in any detail for the rest of the semester. Again, you can easily spend a semester or the rest of your life studying these metrics that look at these models to try and understand these trade-offs between the complexity of models and the tendency of the models to overfit.